Okay, so just to kind of review, let's take a look at H2O really quick. And I'm going to kind of go all the way through. This is just to show you exactly where I want you to be at the end of this unit, which will probably conclude about a week and a half maybe after we come back from break. Okay? So as of right now, you know that the Lewis structure kind of looks like this. It's okay to draw it linear looking. However, you'll notice very quickly that this is not the case, right? First, you should add up the valence electrons, yeah? Hydrogen's 1 times 2. Oxygen is 6. We have 8 electrons to deal with for our drawing. I used up 4 of them by the 2 lines that I've drawn, so I have 4 left, right? 4 left. Hydrogen here is happy. This hydrogen is happy, but the middle oxygen is not happy, right? And it's perfect because oxygen is the other elements, right? That always want 8. It's called the octet rule. And so it's perfect because it has 4 right now, and and I have 4 more for my drawing. So I'm going to put lone pairs above and below the oxygen there. Okay? All right, so this is the structure of H2O. For right now, you're going to realize really quickly, if you open up your molecular geometry chart on your Google Classroom at the very top in your classwork. So go to your classwork. At the very top, molecular geometry chart. Go ahead and open that up. And I want you to search, I want you to look and search. The main thing, though, is that I am not sure if you are going to be able to use that chart, okay, for the test. So let's see if we can get to this level. So this is correct Lewis structure. Let's say 1 point. Another point on the test would be, can you give me the bond angle? Now, we know this isn't going to be linear. This bond angle, it looks like it's 180, but you have to realize over time, wait a second, this isn't H2O. It's going to be tetrahedral-like. So let's say you have H here and H here. And you have lone pair here and here. Now, these lone pairs are shooting out at you and above, out of the board and above. And these lone pairs are back and above, back and up, right? And these two are forward and up. Okay? Now, the thing about lone pairs of electrons, they actually take up a lot of space. Now, this structure that you're seeing here is a lot like CH4. Now, I know that sounds a little bit crazy, but CH4, I know you think it looks like this. But let me draw it kind of like I'm drawing the H2O. Let's take a look at CH4. What if I put the H here and H here, just like the water, and the other H is shooting where like the lone pairs are? So this instead of this lone pair here, right? So this H is shooting out at you and so forward and up, and this is back and up. Okay, so very, very similar, except for water, the H's, these above H's, were replaced with lone pairs of electrons. And don't worry, we're going to be looking at it a lot more using ball and stick model. And I'll show you after this, right after this, I'm going to pass it around. I'll create it for you and I'll pass it around while you're doing your worksheet. So when they're talking about bond angle, it looks like this might be 90 degrees, 90 degrees, 90 degrees, and 90 degrees. It kind of looks like that because it's 360, right? But that's because CH4 is on a flat 2D surface right now. If you are allowed to shoot the CH4 into a 3D world, if you're able to shoot it out into a 3D world, it's not 90. They're able to stretch out more than 90, right? It's close to 90, but they're able to stretch out more than 90. The bond angles for this CH4 is not 90, it's 109.5 degrees. More than 90, okay? It's exactly 109.5. Water looks a lot like CH4, so it should be around 109.5. But let me see. We're looking at this specific bond angle here, right here. This bond angle, it's a lot close to 109.5, which is here. This is 109.5, right, for CH4. So this is going to be close to 109.5. The interesting thing is this is very important. The lone pairs, these lone pairs that are in place of the H's, these lone pairs that are in place of the H's, they actually take up more space than the H's. They take up more space. Like they're bigger and stronger, and like the electrons there are pushing this angle tighter. It's pushing the angle smaller. So for every lone pair, it kind of pushes this angle tighter by 2.5 degrees. So since we have two lone pairs instead of two H's, this bond angle for water is going to be 2.5 less than 109.5, and then another 2.5 less than that. So 2.5 less is 107, and then 2.5 less further is 104.5. So this bond angle is right here on the bottom here, is actually 104.5 degrees for water. I believe your molecular geometry chart says 105 or approximately 105. It's pretty much around 104.5. Okay, it squeezes it. Okay, the lone pairs actually squeeze it even more than the H's would in methane, CH4. All right, so there's a lot of stuff there. For sure, I'm sure water is going to show up as one of your questions on the test. And this is where I want you to get, okay? I want you to be able to draw the Lewis structure. After you draw it, you should be able to tell me that it's bent. The molecular geometry name is bent. You should be able to tell me that it's 104.5 degrees bond angle. You got to be able to tell me whether it's polar or non-polar. And this is going to be polar. And again, we'll get to that. I'm just showing you the end game, right? Like where I need you to get to in order to do well on the exam. Polar or non-polar? That's the question. And this is going to be polar. Everything that's bent is polar. Because one side, hydrogen, the hydrogen side is delta positive. There is a positive charge on the hydrogen because oxygen is more electronegative. So the electrons are always going to be kind of hanging out toward the oxygen. So there's a north and south pole, right? A north and south pole. There's a north and south pole to this water molecule, so therefore it's polar. Okay? And then I need you to be able to tell me the hybridization. Hybridization, if you have one thing, like this is just one one thing attached to one thing, the hybridization will be S. If you have two things attached to it, like maybe like CO2, CO2, by the way, has two double bonds. Okay, so, and we can get to that. We can practice a few times. Okay. The hybridization, since there's two things, it's sp. If you have three things attached, and I'm talking about even lone pairs count. Even lone pairs count. So sp, sp2, sp3, sp3d, like, you know, the orbitals. This is kind of like the orbitals and their hybridization. sp3d2. There's only these 6 options, okay, for the hybridization. So for water, right, H2O, how many things are on that oxygen? So you have like 1, 2, 3, 4. Okay? Each line is a thing. Lone pair is a thing. Okay? So you have 4 things. What would be its hybridization? This is for 1 thing, 2 things, 3 things, 4 things, 5 things, and 6 things. Okay? So your answer for this, because there's 4 things, hybridization is, yeah, sp3. Okay? So can you draw this correctly? And then can you determine bent 104.5 degrees polar and sp3? And possibly without the molecular geometry chart. But we'll get there, okay? So don't freak out. All right, is there one that let's just do a couple of them, just drawing the Lewis structure, going back to yesterday. Does anyone have any one that they would like me to do real quick? And then I'm going to have you just work on your own, okay? What's that? Okay, PO4 3 minus. There is one more thing we're going to have to learn. I'll teach it tomorrow. That some of these drawings, even though you followed all of my tricks and rules, might not be perfect. It might not be the perfect drawing. And you're going to have to tweak the drawing after you learn what's called formal charges. Okay? But as of right now, you just do it based on what I taught you, and then just follow that. Okay? So PO4 3 minus. So far, although I believe this is one of those special ones for sure that you're going to have to tweak. But based on what you've learned and how you've learned it, this is how you're going to do Lewis structure. 5 plus 6 times 4 plus 3. Okay? And you get 32. Let me know if I'm wrong. Okay? 32. So I have 32 for my drawing. I'm going to put P in the middle, and I'll just put the 4 O's. One line, 32 minus 8, 24 left. And I'm going to go ahead and put 6, 6, 6, 6, and be done with it. Did you possibly ask for this because you saw a different answer online? Yeah? Yeah, so this one, everyone, so really good question, okay? And I'm really glad you asked this one. I'm really glad you asked this one because this looks like, based on what you've learned from me, this is correct as of right now. But you're going to learn tomorrow a thing called formal charge. Formal charge, you know? And once you learn formal charge, you're going to have to tweak this drawing because this is not the perfect drawing for PO43 minus. And I'll definitely show you how to do that tomorrow. You can get ahead. I'll post a video on formal charge today, right now. Okay, so if you want, you can try practicing it before I teach it tomorrow. Next. CO? Yeah. Just CO? Okay, so we're looking at 4 plus 6. We have 10. Okay, we're going to put C, and we'll start with just a single bond, right? We'll start with a single bond. That's minus 2. I have 8 to go, okay? And I'm like, all right, 2, 4, 6, 8. Oh no, what's wrong here? Right? This carbon's okay though, right? The carbon's great, it's happy, but this oxygen is not happy. It doesn't have enough. And so it's not that I have extra, it's that I don't have enough. And how much am I short by? I need 2 more here and 2 more here. Right, everyone? So I'm short by what? 4. Now, if you look on the whiteboard, or you can look on the last thing that we did, when you're missing 2, you probably have 1 double bond. Or when you're missing 2, you have 1 double bond. Okay? I keep saying probably, but you have 1 double bond. If you're missing 4, you either have 2 double bonds or 1 triple bond. And if you look on this particular molecule, you cannot have 2 double bonds, right? Because it's just C to O. So you start from the beginning. I would erase all of that, and I would go back, and I would put a triple bond. So from this part, it's not minus 2 anymore. It's minus 6. And I have 4 left. So, every time you add another line, you make up two missing electrons. You make up 2 missing. So by putting 3 lines here, I have 4 left, and I can put 2 here and 2 here. Carbon monoxide. Carbon monoxide. Remember the name? You don't use mono for the first element, but you use mono for the second. Carbon monoxide. And it's not monoxide, double O in the middle, you single O, and it's carbon monoxide. This is the stuff that's coming out of like your exhaust, And there's been like freak accidents of carbon monoxide poisoning, of some people accidentally leaving a baby for just like 30 seconds at the back of a car, and then they're gone, So if you ever, when you have babies yourselves, you got to be cognizant of that. It's such tragedy, right? Any other ones that you'd like me to do? Yes? Which one? NH3. Okay, let's do NH3 really quick. We're looking at 5 plus 1 times 3, okay? 8 total. You have N in the middle, and I'll just put H as like a triangle. We're going 2, 2, 2. That's minus 6. I have 2 left. This hydrogen, all hydrogens, remember again, as soon as there's a line to it, it's done. Because hydrogens can only have 2 and 2 only. Before I forget, because I keep thinking about telling y'all, and I keep forgetting, hydrogen is always 2. Happy with 2 and never more than 2. It can't. There are other exceptions. Beryllium, and I didn't mention this yesterday, so that's why I'm mentioning it now. Beryllium is 4. Okay, beryllium actually is happy with 4, and it can't really have more than 4. And boron is always happy with 6. I do apologize for not mentioning this yesterday, but this is crucial, okay? So if you ever run into these particular 3 special ones, just know, like, wait a second, boron's not happy. You're like, it only has 6. Oh no, boron is special. It's okay with 6. Okay, so you have to remember that. If not, you're going to be like running around in circles, you know? So NH3, everything's good except I have 2 left, and nitrogen is not happy. So you're going to put the lone pair here on nitrogen. Okay? Yes, Sean? Not as of right now. In actuality, NH3 is going to look like this, though. It's going to look kind of like a 3-sided pyramid with lone pair at the top. You know, like I kind of drew like a 4-sided pyramid here somehow, but let me get rid of these dots. I'll show you. I'm gonna build the stick models for you. It's a trigonal. It's a pyramid, right? That's 3-sided. A pyramid. You know, like not the pyramids of Egypt. Pyramids of Egypt, I believe they're 4-sided. This is a 3-sided. Are some 3-sided? 5-sided. Some of them. 4-sided. So this is a 3-sided pyramid. So it's a trigonal. Because triangular, trigonal pyramid is the name for it. It's also a lot like water because and methane. It's still the same family, the family of tetrahedral, but there's a lone pair that's taken up instead of a H, right? So what might you guess the bond angle to be? That's hybridization, but what's the bond angle, you think? Remember the CH4 was 109.5? It had 4 H's, it's 109.5. But one of the H's now are replaced with a lone pair, and it's going to squeeze it all down by 2.5. So what's the bond angle? 107. Okay. Hybridization, I heard it earlier. What is it? sp3. Amazing. And then polar or non-polar? Is there like a north and south pole to this thing? We'll get into polarity more tomorrow, okay? It is polar, right? At the top of the pyramid is different than the bottom of the pyramid. The bottom of the pyramid has all these H's, and at the top of the pyramid it has a solo nitrogen with a lone pair. This is polar. There's a north and south pole. When it's non-polar is when everything looks symmetrical every which way. You can flip it upside down. You can keep it right side up. You can flip it on its side, on its back, and you can spin it in a circle, and it's going to be the same. That's non-polar. Okay?